Okay, let's keep going on waves. So waves on a string. So we talked about how the speed of sound, the speed of sound in a material, or the speed of the wave, depends on the medium. So for a wave on a string, we have this thing. So let's talk about that. So the speed of a wave on a string depends on the tension and the linear mass density of the string, right? So like a rope would have more mass per unit length than like a piece of floss, right? And tension is right how tightly the thing's taut. So you get something called a standing wave when you do a wave on a string, and the first part of a standing wave on a string is this fundamental. And that's the fundamental. What did I want to say? Oh, yeah, that is an antinode, and that is a node, right? So what's actually happening here is you have a wave going this way, and it reflects off here, and it goes this way, and you get constructive interference, which gives you an antinode, and destructive interference, which gives you a node. And so there's no movement right here because it's, fixed at that point. Okay, so this fundamental is also called the first harmonic. And something you'll see is when you say, okay, how many wavelengths is that? You can imagine that's the rest of the wave, right? And then that whole thing would be a wavelength. So from that, you can see that the length of the wave, right? My bad. The length of the string is equal to half a wavelength. All right. And so then when we say, okay, well, what is the frequency of this fundamental? V equals F lambda, right? So F is V over lambda, and lambda is 2L. Okay, so this is the fundamental frequency, or the first harmonic. The second harmonic looks like that, and L is lambda, right? So this is V over lambda, so V over L. And dude, that F2 is equal to 2 F1, okay? This is the second harmonic, okay? And here it is. N is the number harmonic, and that's the fundamental. And then that's just the integer that corresponds to the number harmonic. There's also a word overtone. So you have first harmonic, second harmonic, third harmonic, or fundamental. So fundamental, and then this would be first overtone, and then the third harmonic is the second overtone. So hopefully you see the pattern there. So fundamental, and then start counting overtones, or F1, F2, if those are harmonics. Okay, cool. So that's one way to make music is on strings. Another way is with pipes. Okay, so when they talk about closed and open pipes. The closed pipes are only closed on one end. You know what, the open one's probably easier to start with. Okay, so let's do open. And open means it's open on both ends. Okay? And what you see here is that if you imagine your little molecule of air that can, jostle back and forth, right? These are longitudinal waves, right? Compressional waves. you can imagine that these guys can move a lot, right out here. And so it turns out that an open end is a displacement antinode. Okay, I say displacement antinode because you often talk about displacement waves and pressure waves, and they're absolute opposite. So a displacement antinode is a pressure node. And it's a little bit more complicated than I want to get into right now. But we can draw this. An antinode would look like that, right? That's where the biggest thing is, and here's a node, and there's an antinode. So this is the fundamental for an open pipe, and if you look at how much of a wavelength that is, you can imagine, right? That would be a whole thing. So L is, in fact, lambda over 2. And so you get exactly the same kind of thing as the wave on a string. Okay? So that's the first harmonic. And then the second harmonic, which is the first overtone. I don't really have a rhyme or reason for why I'm using these colors, so don't read too much into it. Okay. We know that these need to be antinodes. And so it looks like this. Not awesome picture, sorry about that. But it ends up being one full wavelength. And so your F2 is, oopsies, 2F1. So it's the same as a string. Now, closed gets fun. So this is what a closed pipe looks like. And really, it's just closed on one end. So here, we need a node, a displacement node, right? Because the molecules can't go anywhere there. But here they can. And so we get an antinode at the open end and a node on the closed end. And when you look at that, you say, oh my gosh, that's not a half a wavelength. That's actually a quarter of a wavelength. Okay? So our fundamental frequency here is V over 4L. All right? Now, this is where it gets a little bit interesting. If you try to draw the next harmonic, and it has to have an open thing here and a node there, you will get something that looks like this, and that is 3 lambda over 4. So our F3 is V, that's 4L over 3. So that is our, ready, first overtone here for a closed pipe is a third harmonic. Okay, fundamental is the first harmonic. Our first overtone is a third harmonic. So closed, there are no even harmonics. So that's a fun fact. All right.